You know, I'm going to switch. What's up, everybody at home? There we go. That just sounds better. Can you hear me better without that? It's not the cloth. All right. People are going to talk about the development of the modern, there we go, the development of modern atomic theory. And don't worry about this where it says we're going to make a comic book. That's something that we used to do. I just still the old PowerPoint, okay? All right, now, how are we going to work on this? Here's how we're going to work on it. You don't have to write all this stuff down, okay? You don't have to take a note on every person. This slideshow will always be here, okay? There will not be questions on your test that say, this scientist did this scientist did this. There may be a couple, but I'll emphasize those later. Does that make sense? So let's get started. All right, the first guy was Democritus. All right, we're talking about a long time ago. Democritus, Greek philosopher, this is talking about BC era. He said, hey, everything's made out of tiny things. And he had an atomic theory, and the word was atomos. And he said, atoms are tiny little things, and they're solid and indestructible. And that's not quite true, but it was pretty good thinking for back then. And he said different things contain different atoms. And unfortunately, that theory was rejected. Do you know what theory it was rejected for? Anybody have any idea? Ptolemy said that everything on Earth was really just made up of four things: earth, wind, fire, and water. And that was wrong, okay? So we're talking about thousands of years later, literally like 2,200 years later, we get to this guy named John Dalton. So in 1803, Dalton, this is really the beginning of chemistry. And we're talking about chemistry now being separated from alchemy, chemistry being a hard science, okay? So he had the first modern atomic theory. He said all matter is made of atoms, okay? And then he said all atoms of an element are identical, which is not quite true because of isotopes, but is very accurate because of protons, okay? And different from other atoms, all right? And atoms cannot be created, divided, or destroyed, which isn't quite true, but still a very good idea. When we're talking about dividing atoms, we're talking about nuclear power, we're talking about fission, we're talking about radiation, we're talking about things that wouldn't come along for well over 100 years after this. So his idea about atoms was really, really good. And he said atoms combine in whole number ratios to form compounds. How do you think he did this? Like, our country is only like 28 years old when he came out of this. How do you think that he did this? I'll tell you, one of the things he used was water. And we had electricity at this point in time, especially in battery power. So what he did was he could separate water. We could do it in here pretty easily with a battery. He would separate water with a positive charge and a negative charge from a battery. And he noticed that it always separated in a 2-to-1 ratio, okay? And that would be the hydrogen gas to the oxygen gas. So he knew that the formula for water was 2 parts something, 1 part something else. Does that make sense? So that was really good. All right, then Mendeleev, this guy comes along. We'll see a video about him. I'll post a video about him. Okay. Really, really smart person. He developed the modern periodic table of the elements. All right. Mendeleev's table, you'll see in some notes later, was super accurate, and it came out in 1872. Okay. After Mendeleev, all right, so first, now here's what we got. We got John Dalton. He said everything's made out of atoms, and they form everything in whole number ratios. And then Mendeleev takes all the elements that we know, and he arranges them into a table that's very, very useful. And then J.J. Thomson comes along, and he discovers that when we look at these atoms, there are charges in the atoms, and he said the atoms are full of these negative charges, okay? The atoms are full of these negative charges. And he knew that electrons were very, very light, the charge to mass ratio. But his model of the atom, he called the plum pudding model. Now, what you and I would call it today would be like a chocolate chip cookie model. He said you have an atom, and there are these little negative charges placed in there, like plums in a pudding. But we don't eat plum pudding, we have chocolate chip cookies. So he'd say, well, it's like chocolate chip batter, and the chips are in there, they're kind of like the electrons are in there, okay? And that's pretty much true, except for we can define the spaces they're found better now. Then, Robert Milliken comes along. How do you know Robert Milliken's a really smart person? What's your guess? What about this picture would tell you that Robert Milliken was super smart?
Oh,
Mm-hmm.
He just looks smart.
Just looks smart. How about he's standing with Einstein, and they're co-workers, right? You got to be a pretty smart person to work with Einstein. Milliken was a genius. He was a super genius. What Milliken did was weigh an electron. And you're like, what? How do you weigh an electron? He did something called the oil drop experiment. And just to make it really, really simple, had a really thin stream of oil, okay, that would drip through like a glass tube. And beside of that very, very thin stream of oil, where he would move like a very controlled amount of oil. Ashlyn, you with me? Are you with me? Okay. Y'all shut your computers, okay? Because I'm giving you this right now. So this little bit of oil is moving through this glass tube, and then he puts a charge beside of it. Because we knew about Coulomb's law and things like this. And remember, Milliken knew that the electron was negative from the guy that came before him, J.J. Thomson, right? So Milliken knows electrons are negative. He knows they're in atoms. So he takes a controlled amount of oil, and he drips it through a tube, and he puts a charge beside of it that moves the electrons off of it, okay, using Coulomb's law. Then he reweighs the oil. Now, if you knew approximately how many electrons you should have in the oil, and you knew that you moved those electrons off, then you could come up with the weight of an electron. So we're talking about 1909, calculating the mass of something that's 9.1 times 10 to the negative 28 grams, which was pretty accurate. So that's pretty much how that was done. Okay? Then after him, this guy, Ernest Rutherford, comes along. Rutherford does what's called the gold foil experiment. You will see that. I will show that to you later. It'll be part of some notes that we film and do for everybody at home as well. The gold foil experiment was crazy, and it was a surprise to Rutherford. Rutherford said, hey, these atoms that we all know about now that have these negative charges, these atoms are mostly empty space, okay? And he was going to prove that to everyone. He got a sheet of foil, of gold foil. He had it stamped very, very thin as it could be made in 1911. And he put this gold foil up, and then he got basically a little gun that could shoot particles of radioactive decay, charged particles, through the foil. And then he put some film around the foil. And he was going to show that these particles went straight through the foil, and that they hit the film. Where the charged particles would hit the film would be developed there, and it would leave like a little white spot on the film. Does that make sense? Do you know what I mean? Like old school film that you would use in a darkroom? Well, what he found out was that the particles he was shooting through the gold foil, not all of them went straight through. About 1 in 3,000 bounced backwards or went off in some direction. So he realized that atoms had a solid center. Now, this is a really simple, oversimplified version, okay? But he's expecting the particles to go straight through. Then some of them bounced off at an angle, and some of them even went backwards, okay? So what must an atom have if it can cause these nuclear bullets to deflect. It must have a solid place in there. So he ended up discovering the nucleus, okay? So Ernest Rutherford discovers the nucleus by ricocheting particles through a sheet of gold foil. In order for it to ricochet or to go off at an angle or to bounce backwards, there has to be a little solid chunk in the atom, right? So now we're crawling along here. Now we're crawling forward. We know that atoms make up things in whole number ratios. We know that atoms have negative charges in them. We know those negative charges are super, super light. And now we know these atoms with negative charges have a solid center in them, so solid that it can deflect particles, okay? So then this guy, Henry Moseley, comes along. He's a super genius. He's very young. And he rearranges the periodic table, okay? He determined the atomic numbers of each atom. In other words, how many protons were in the nucleus. How did he know there were protons? Because of Ernest Rutherford's work with the nucleus. So Henry Moseley, super genius, comes along at a very, like in his young 20s, determines the atomic number, which slightly changes the order of the periodic table. Okay? And the atomic numbers up here on the periodic table are all due to his work. Okay? In 1913. And he was going to win a Nobel Prize, no doubt. But he was shot and killed in World War I at Gallipoli, which was probably a bad idea. If you're a government and you have one of the smartest people in your country, I think you should give them a calculator and a pencil instead of a gun. But Henry Moseley was shot and killed at Gallipoli in trench warfare. All right, that's not what we did with our scientists for World War II, is it? Did we say, thank you, Einstein? Thank you, all you other scientists, for coming to the United States. Here's your guns. No, we gave them a bunch of money and computers, right? Does that make sense? Okay. All right. Niels Bohr comes along. You definitely heard of Niels Bohr. 1913. He starts calculating electrons and where we could find them in orbit around the nucleus of an atom. And you come up with the Bohr model. What Bohr is doing right here is taking physics and chemistry and putting it together. Okay? He created the planetary model of the atom where the electrons move in orbits around the nucleus. And his math was really, really on it. And his math, you'll learn later, matched the periodic table perfectly. And just like the other lab we did today, the Bohr models are made from Niels Bohr's math. And notice how the Bohr models fall perfectly into place on the little game board, right? Okay? So electrons move in specific circular orbits. Now they don't really do this. Okay? And there's a really good story here about Niels Bohr and Werner Heisenberg. Okay. Werner Heisenberg. Heisenberg was a Nazi. Heisenberg came up with what's called the Heisenberg uncertainty principle. And he basically said, Bohr's model can't really say that these electrons are moving around in circles and orbits, because when we start to do the math here, you can either find out where that electron's going to be, or you can find out its velocity and momentum. You can't find out both at the same time. And this really leads us to understand that electrons have wave-particle duality, which is something you'll understand or hear later. Then the last person, so what have we got so far? Dalton saying atoms, everything's made of atoms and whole number ratios. J.J. Thomson coming along and saying, hey, there's electrons in there. Milliken weighing the electrons. Rutherford discovering the nucleus and the protons. Henry Moseley rearranging the periodic table and saying, hey, what defines these atoms are their protons. Niels Bohr taking the electrons and trying to calculate where they fit and how many of them there are. He's largely accurate, but for one idea that he doesn't understand that these electrons are just sometimes waves. Heisenberg comes up with quantum physics and says, hey, we've got wave-particle duality. And then now we've got one more particle left that hasn't been discovered. What's that? We've got protons, electrons. What's missing? The neutron. James Chadwick. This is much later. This is 1932. He discovers the neutron, and he develops our modern theory of the atom, which is the electron cloud. Okay? He comes up with the neutron saying the weights of these atoms. There has to be something, another uncharged particle coming in here. He discovers it, proves it exists. I'm sure he gets a lot of credit for working with isotopes or defining what an isotope is. He has to. And then he uses Bohr's math and Heisenberg's physics and says, this is really our model of the atom, a cloud of electrons appearing and disappearing in fairly predictable places. And that's where we are today. And this is a funny little story I usually tell with this. But that takes us to where we are today. So that's how we got from nothing to where we are. All right? That takes us all the way back from Democritus to James Chadwick.